Much for the introduction. Okay. When I was thinking about the topic of my presentation, I decided to tell you about the direction I work most on so far. So I hope you will enjoy it. I will be speaking about Clique-width of atoms and coloring for a hereditary graph class. Yeah, so let's start. Many hard graph problems became tractable when restricting inputs to some graph class. So we restrict ourselves to particular subclasses of hereditary classes. So let me tell the definitions. We say that a graph class is hereditary if it's closed under a vertex deletion. And working with hereditary classes allows us to do a systematic study, as every hereditary class can be characterized by set of forbidden induced subgraphs. And for graphs with one forbidden induced subgraph H, we use the term H-free. So H-free graphs are graphs that doesn't contain H as an induced subgraph, and we use similar notations for many graphs. So if a graph is H1, H2, and HK-free, we use this notation. So here is a quick example. Here you can see one graph which is disconnected. It's a disjoint union of path on 1 and 4 vertices. So this is another notation I will be using in my slide. And let's look at middle example. This is P1 plus P4 free, because you see that if you take any path on 4 vertices, there is no remaining vertex which is non-adjacent to it. So such a graph is P1 plus P4 free, but the right graph is not. So you see the P4 and induced P4 and P1 depicted in blue color. So this is quite a main definition in my talk, because I will be speaking most of the time about H-free graphs. And yeah, let's move to first part of my talk, which is about coloring in H-free graphs. So I start with recalling what's coloring. So coloring of a graph is an assignment of colors to vertices, such that no two adjacent vertices get the same color. And I will be speaking about two particular coloring problems. The first one is K-coloring, which asks for a given graph whether there exists a coloring of it which uses at most K colors. And then I will be speaking about list K coloring, where additionally each vertex has a list assignment of allowed colors, which is a subset of colors 1 to K. And we ask if there exists a coloring that respects these list assignments. So K coloring is a special case of list K coloring. And yeah, just again, look at a quick example. Here we have instance of list-free coloring, for example. And the solution may look like that. So you can choose 2, 3, and 1 here, and you obtain proper coloring. So this is a solution. I hope this is clear, and you probably knew all of it. Yes, there has been an extensive study about the computational complexity of K coloring on H-free graphs. So thanks to the earlier results, we know that for any K, which is at least 3, K coloring on H-free graph is NP complete if H contains a cycle or an induced glow. So what remains is to consider the case where H is a disjoint union of paths. So again, you can see here an example of a disjoint union of 2 paths on 2 vertices, 1 path of 3 vertices, and 1 path of, on 4 vertices. And a special attention has been paid to PT-free graphs. That is graphs without induced path on T vertices. And what's known now is that the question whether K-coloring is polynomial or NP-complete is open only for free coloring and list free coloring for past or PT-free graphs on for at least 8. And recently there has been a result which is not polynomial or NP-complete, but it's quasi-polynomial, so the best known for us for any PT-free graphs and free coloring and list free coloring. And what's also interesting in this table is that for coloring on P6 free graphs is polynomial, whereas list for coloring on P6 free graphs is NP-complete. So this was quite a these were quite nice results, and it's nice to see that the complexity can differ in these cases. Yeah, when H is disconnected, so as I said, H is a disjoint union of paths. There are also many results, and currently we know that list free coloring is polynomial time solvable on H free graphs if H has at most 7 vertices. And yeah, this theorem is a combination of few independent results. And 2 years ago, we did the last piece by finding a polynomial time algorithm for P3 plus P4 and P2 plus P5 free graphs. Yeah, to obtain similar results on 8 vertices, there are 2 remaining cases. But the case with P8 free graphs is really interesting, difficult, and yeah, interesting by its own. Yeah. So maybe in closer look, forbidding another subgraph, here a small cycle is one of the approaches how to attack the problem. So you may split the difficulty into 2 easier but still quite complicated parts in such a, yeah. Yeah, so in such a way, for example, the current best results of P7 free graphs was solved. So at first, additionally, a triangle was forbidden to P7 free graphs. And later a result for P7 free graphs, which contains a triangle where has been proved. So this is one of the approaches. There are many results in this direction. I didn't definitely mention all of them, but for example, if you looked on these results, if you take any PT free graphs which is additionally C4 free, we know that free coloring is polynomial time solvable. Or our recent results state that free coloring of 2P4 and C5 free graphs is polynomial. Yeah, so if there are some questions to this part, you can ask here or later after the talk.
And I have a question. I have a question. Just how you prove those results. Do you actually find a structural characterization of these graphs that have no PTs, and then show that you can color them quickly? You have to do.
Yeah, actually, usually you prove the structure of those graphs, so that's why having bigger T is much more difficult because there is less structure, let's say, and so usually you find some structure, and then you do some branching, some pre-coloring, and you end up
decomposing with or something. Yeah.
Sorry.
Then you decompose these graphs into and then do each part.
Yeah, you decompose them and you end up with 2 SAT, or where each vertex has only 2 colors available, and then you know that it's polynomial. But it's heavy structure dependent.
It sounds hard. Thank you.
Yeah, I think it is. Okay, so I will move to my the second part of my talk, which is about graph parameter, which is called Clique-width. And the motivation behind is that we would like to solve more problems at once, not just considering one by one, but yeah. And graph parameters, so like Clique-width make such results possible. So you will see in a while. So at first, I will start what is Clique-width. So Clique-width of a graph is defined as the minimum number of labels which are required to construct our graph using the following operations. You can create a vertex and give him a label. Then you can take the disjoint union of two labeled graphs. You can rename all labels I to j, and you can connect all vertices with label I to all vertices with label j. We say that the graph has bounded Clique-width if there exists a constant which upper bounds the Clique-width of each graph in the class. Let's look at the Barmak example. I would like to ask what is the Clique-width of a complete graph. So how many labels do we need to construct a complete graph according to this definition? So I will let just 1 minute. If somebody would like to answer, or I will answer in a minute. So yeah, it's 2. We all the time we at one vertex give him some label and then connect it with all other vertices and rename its label to the labels of the other vertices. So if you have Clique-width on at least 2 vertices, you need 2. But it's bounded also. So I wanted to show this example. Is probably quite easy, but yeah. And maybe I want also to add that in case you haven't known the Clique-width before, you don't need to remember the exact definition to follow my talk. Instead, it's good to remember that having bounded Clique-width is a very useful property, and I will show you right now why. So if you restrict our graph class to bounded Clique-width, then large collection of problems become polynomial time solvable because of, or thanks to results of Krusell, Makowski, Rodix, and many other researchers who added some more problems. So having bounded Clique-width is a really nice property. And there are lots of results on the boundedness of Clique-width for hereditary graph classes. For example, there is a survey by Dobrowski, Johnson, and Paulusma about the boundedness of Clique-width of H1, H2, 3 graphs, and they left only 5 open cases here. Yeah, but what to do if Clique-width is not bounded? So there's one of another approaches. Maybe use atoms. I will tell you in the next slide what atoms are. If Clique-width is not bounded, we still have some tool how to investigate some problems simultaneously. And so if we work with hereditary graph class and restrict ourselves to atoms, then there are some problems which are polynomial time solvable on the whole class, if they are polynomial time solvable only on atoms. And this set of problems is much more smaller than the set here, but still it contains some well-known problems such as coloring, maximum independent set, maximum induced matching, and so on. Yeah, so by combining those 2 results, we obtain that if a hereditary class has bounded Clique-width of atoms, then those bottom problems are polynomial time solvable. And yeah, that's what we will be doing. So what is an atom? An atom is a connected graph with no Clique set. So in other words, you cannot find any clique such that if you remove it, your graph will be disconnected. So this is quite easy definition, but important in my talk. And yeah, we can ask quite natural question. Are there any hereditary graph classes of unbounded Clique-width whose atoms have bounded Clique-width? So in other words, can atom approach help here in, yeah? And the answer is yes. So we can look at split graphs, which is a class of graph which has clique on one side, independent set on the other side, and an arbitrary relation between them. And Makoski and Rotic showed a long time ago that this graph class is unbounded Clique-width. But think for a while about atoms, how atoms look like here. So yeah, atoms of split graphs are only clique because otherwise the clique part would be a clique cut set. So on the one side we have split graphs, they have unbounded Clique-width, and on the other side, atoms of split graphs are cliques, and we already know that they have bounded Clique-widths. They have Clique-width too. So that's one example of such a class where this approach may help. There are also other examples, other results for graphs without even cycles on at least 4 vertices and one more graph. And we would like to forbid as few as possible. So the question is, what if we forbid just one graph? And it has been shown that this approach does not help here in H3 graphs because it's equivalent there to have bounded Clique-width and bounded Clique-width of atoms. And also H3 graph with bounded Clique-width are well structured before free graphs known as cographs. So it's quite easy here. But what about if we forbid 2 graphs? And there has been another result about C4P63 graphs. Atoms that they have Clique-width. They have bounded Clique-width, but these graphs have unbounded Clique-width. So this particular example gave us some hope that this approach may help in graphs where we forbid to induce subgraphs. So our main question was to ask which H1, H3 graphs of unbounded Clique-width have the property that their atoms have bounded Clique-width. And that's what we were doing. We were investigating these questions. And in the end, we found some results. So we found one bounded case. I will tell you a bit more about it just a little bit later. And then also we found many unbounded cases. And yeah, it's not important now to follow which graphs are there. It probably doesn't tell anything. But what's important is that we classified Clique-width of all but 19 cases of H1, H3 graphs. And as this area was widely open before, there were infinite number of cases. So ending with something like 19 is pretty good, even though it may seem that it's a huge number of open cases, but we are happy that it's bounded number. And moreover, 10 of these open cases came out from just bounded the question about Clique-width and unboundedness in graphs, even not in atoms. I said before a while that they left 5 open cases, and now I'm writing here 10, and I will explain just in next slide why is it. So we have 10 open cases from the boundedness of graphs, and 9 more where the Clique-width is known to be unbounded for such graphs, but we don't know about atoms. Yeah. So I promised I will tell you about those 10 cases. So when you are working with Clique-width of graphs, you usually don't care about constant number of vertices, because if you delete or add constant number of vertices, it doesn't change that your Clique-width is unbounded or not. And also similarly, you are allowed to do complementation operations. So you can replace edges with non-edges and vice versa. And still you didn't change or don't change the boundedness of Clique-width. But neither of these operations preserve the atoms. So when working with atoms, you need to be more careful about more careful with performing these operations. So in particular, in contrast to graphs, we showed that there are classes whose atoms have bounded Clique-width. So for example, this graph class, which flows from the known result. But we showed that there is a class of unbounded that if we take its complement, so it is unbounded Clique-width. So we need to be really careful with such operations. So therefore, the mentioned 5 open cases for Clique-width actually makes 10 open cases for Clique-width of atoms, because we cannot consider these 2 cases as the same. So it's good to tell at least some of proofs. So I decided to tell you now a little bit more about our bounded case. So we proved that the class of 2p2 and paraglider, I will be called this graph paraglider, 3 atoms as bounded Clique-width, and it was known that this class of graphs is unbounded Clique-width. And yeah, so at first we split our proof into 3 cases, similar as I said before with coloring. So in the first case, we assume that our graph contains an induced cycle on 5 vertices. Okay, if it's not the case, then we can assume that our graph is additionally C5 free. And again, we split it into 2 possibilities. So we say, okay, such a graph contains an induced cycle on 4 vertices. And if it's not the case, then we know that our graph is C4, C5 free additionally, and such a graph is known to have bounded Clique-width. So we need to solve these 2 cases. And in both cases, we fixed one of the induced cycles. We know that they are surely present in our graph. So here you can see a picture. And we start to analyze the neighborhoods of this graph. So again, we would like to find a structure of such graph classes and see what we can do with it. So at first, we all can observe that as our graph doesn't contain 2p2, then all vertices have distance at most 2 from our graph, from our base cycle. Otherwise, we can just take an arbitrary edge from the cycle, and then you will find another p2 somewhere else. So that's the first observation. So we partition our graph into three levels, and from the same reason, we don't know that the second neighborhood is an independent set, which is quite nice for Clique-width. Okay, so we partitioned the neighborhood, the first neighborhood, into sets according to which vertices they see in the base cycle. So for example, the red set are vertices which see exactly this one vertex in the cycle. And what we would like to end up with is to end up with some nice relations. So for example, some of these sets are empty or contain just small number of vertices, or there are cliques and there are really nice relations between them. So that's our direction. And yeah, so for example, you can think of that there are quite easy arguments for the sets or for the vertices. Okay, let's say it in the other way, that there are no vertices in our graph which are connected just to one vertex of our cycle, or to adjacent vertices of our cycle, because then such a graph is again not 2p2 So we easily cross out those sets, and we need to do something more with the other one, and the proof is quite technical, so I don't want to show it here. But instead, I will show you maybe where atoms helped in this approach. So because everything else we could do without atoms. So it's I think it's useful to see where they help, and also it's really great that there is a nice example from the second part where it can be nicely seen. So after a while, we came up in the situation where we have just our base cycle and 4 other sets, A, B, and C, A, B, C, and D. And what we know is that the set B and A are independent sets, D as well, and C is a clique. And we also know that there are all edges between AC, BC, and AB. So it's quite nice structure, but we don't know, unfortunately, anything about D. So we know something, but we don't know relation between D and C. We know that D has no edges into A and B, but it can have, we don't know anything about edges into C, and it's not enough for Clique-width to become unbounded. So you saw an example with split graph where it is exactly to have independent set clique and arbitrary relation between them, and such a graph is unbounded Clique-width. But what's really great here is that C is a clique. So you may now see that there cannot be any vertex in our set D, because otherwise C would be a clique cut set. And now we are done, because we know that D is empty, and now we have really, really nice relation here just for other vertices, and we can conclude safely that Clique-width is bounded here. So yeah. So if there is any question to this proof, you can ask again here or later. And I would like to show you also one of easy unbounded construction, just to see how unbounded Clique-width may be proved. So we want to prove now that 2p2 and house-free atoms have unbounded Clique-width. And how do we do that is that we take some graph we already know. So it's split graph. We know that it has unbounded Clique-width. I said that if we add 2 more vertices, it doesn't change anything. So we add 2 more vertices which are non-adjacent to each other, but complete to the rest of the graph. And I would like now to claim that this is an example of 2p2 house-free atoms, and it has unbounded Clique-width. So it has unbounded Clique-width. We already know it because split graphs. Then the question is if it's 2p2 and house-free. So it's 2p2 free because split graph, another characterization of split graph is those are 2p2, C5, and C4 free graphs. And these vertices cannot at an induced, these vertices cannot change anything here. And after a while, you can see that this graph is also house free. You can see it in complements, or you can find where there are C4s here, cycles on 4 vertices, and you see that you cannot create house. Okay, and the last question is it an atom? And again, so you would like to prove that it's not an atom, you would like to find a clique which disconnects the graph. But here you see that you need to remove both these vertices to disconnect our graph. So it's an atom. And in such a way, we proved that this class of 2p2 house-free atoms have unbounded Clique-width because we found some example which had it. And yeah, usually we modify the unbounded constructions for Clique-width of graphs, which were already known, and we tried to make them, change them to atoms, as I show here, for example. So I promised at the beginning that in the end I will tell you open problems. So here those are the 19 open problems, and these with star are open even for Clique-width. What we shown that actually these two cases are equivalent for atoms, so you can say that there are 18 open problems. I said 19, but it doesn't matter really much. And maybe just to pick some, if you forbid P5 and path on 5 vertices and such a graph, there is a big chance that such graph can have bounded Clique-width of atoms, because there is a result already known result by Malyshev and Novotná that coloring on this graph class is polynomial time solvable. So we would guess that we could try this open case to show that it is bounded Clique-width, but yeah, who knows? So that was for my talk. At the end, I put there two pictures of our working group. On the right picture, we were solving together the Clique-width problem in Durham, and in the left pictures, there is a part of our group after finishing the writing of the paper about free coloring of those two P2 and P5 free graphs. And another co-author is not visible because he is staying behind the camera, and in that time it was straight hit by the snow. So, so we have quite nice memory to those two pictures and to those two collaborations. So I think that in this time of online working, it's nice to put pictures of co-authors as well. So yeah, thank you very much for your attention, and I'd be happy to hear some questions.
Thank you so much, Jana. Maybe we can all unmute ourselves now and clap for Jana. Yeah, so if anyone has questions, now would be the time.
I have a question.
Mm-hmm.
About slide number 14.
Mm-hmm.
So you have this script S. I don't know what the script S is. Did I miss the definition?
Oh yeah, no, I didn't tell you because I wanted to put this table just for the impression how such results can look like, but I didn't know what those letters mean. So as is a union of paths and subdivided cliques, subdivided clause. So you have yeah, you have claw, and you can subdivide each. Yeah, you can subdivide each edge arbitrary times. So,
okay. Okay, thanks. Thank you.
Thank you.
So one question I have, just looking at this list, is sort of, when you're showing unbounded clique width, were you able to come up with sort of a unified construction that was able to take care of many of these cases? Or was it just sort of the same ideas, but sort of, this is one construction, this is another, etc.?
Yeah, usually we had some constructions which were able to cross out more cases. But still, I'm not sure now about precise counting, precise number, but we had, I don't know, 15 constructions for 15 unbounded constructions or something like that. But yeah, usually these constructions cross out many cases.
Maybe I have a question. Which one of the open problems do you think is the hardest, except for the ones that have unbounded clique width?
So, sorry. Yeah, it's really hard to say. So I was thinking that maybe one of those first two. Yeah, I think that maybe the first one. But maybe I just don't see a good idea how to approach it. But yeah, for me, I think those first two are harder to prove than the last two. But it's maybe also that they have unbounded clique-width, or I don't know. Maybe those last two would be easier candidates for bounded clique-width, and those first two for unbounded clique-width. But who knows?
If there aren't any more questions, maybe we can just clap one more time, and before we end the recording and go over to the next part. Thank you so much, Jana.